Every smartphone in your pocket, every AI supercomputer, every advanced data center, and even modern fighter jets, they all depend on one tiny piece of silicon. But actually creating that silicon, it is without a doubt one of the most difficult, mind-bending manufacturing processes humanity has ever come up with. I mean, we're talking about billions of transistors, each one measured in billions of a meter, that have to be etched onto a single chip with absolutely staggering precision. At this microscopic scale, a single mistake smaller than the width of a virus, poof, it ruins an entire wafer and instantly destroys tens of thousands of dollars. The margin for error is literally zero.
For years now, we've watched the world's biggest tech giants fiercely compete to design faster, more efficient chips. You know the names, right? Intel, AMD, NVIDIA, Apple, Qualcomm. They pour absolute billions into research and development. They're the titans of our digital age. But when you look at the other side of the equation, the actual physical creation of these chips, there is this massive, glaring missing piece of the puzzle.
Despite all the headlines and all the billions spent by these famous tech giants, you kind of have to ask yourself, who actually stands behind them all? Who is providing the tools that make their incredible designs a physical reality?
Welcome to this explainer. The answer to that question is a company most people have never even heard of. They don't design processors, they don't manufacture smartphones, and they don't sell computers. And yet, without them, the entire modern semiconductor industry would basically grind to a complete halt. We are talking about the undisputed, indispensable powerhouse behind the world's most advanced microchips.
That company is ASML. Tucked away in a quiet town in the Netherlands, ASML has quietly grown into one of the most strategically important businesses on Earth. Because they don't make the chips themselves, instead, they build the staggeringly complex machines that make the world's most advanced chips possible. And I want to be super clear here, these are not your run-of-the-mill factory tools. They are among the most complex machines ever engineered by human hands, containing hundreds of thousands of components sourced from across the globe. And for the absolute most advanced version of these machines, ASML has zero true competitors. None.
Okay, let's dive into this timeline to see how they pulled this dominance off. You have to go back to 1984. Back then, the semiconductor industry was completely dominated by massive American and Japanese companies. ASML, they started out as just a small joint venture between the Dutch electronics company Philips and a machine manufacturer called ASM International. Honestly, very few people expected them to survive, let alone lead the market. Their early years were incredibly difficult. Super limited resources, highly skeptical customers, and rivals with incredibly deep pockets. But then they made a pivot that literally changed history. Instead of trying to dominate every single category of chip-making equipment, they put a relentless singular focus on one critical process, lithography.
So to understand ASML, we have to understand lithography. Think of it like a ridiculously advanced form of printing. But instead of using ink, the machine uses light to project highly intricate circuit patterns onto silicon wafers. And we aren't measuring in inches or millimeters here. These patterns are measured in nanometers. It's kind of like trying to draw a highly detailed city map on a canvas the size of a single human cell.
For decades, the industry moved forward by just refining this exact process. To make chips more powerful, you have to squeeze more transistors into the exact same physical space. To do that, you have to make every feature smaller. And the physics rule here is pretty straightforward. Making features smaller requires using shorter and shorter wavelengths of light. Engineers just kept pushing the existing technology to its absolute limits, squeezing out more performance year after year. But eventually they hit a wall, a literal physics wall. Traditional deep ultraviolet lithography reached its physical limits. They couldn't go any smaller. They needed a massive, seemingly impossible technological leap.
The theoretical answer to that problem was extreme ultraviolet lithography, or EUV. Now, in theory, EUV promised dramatically smaller chip features. But in practice, a lot of experts thought it was quite literally scientifically impossible to commercialize. Why? Well, because EUV light is so incredibly delicate that it gets absorbed by nearly everything, including ordinary glass. You couldn't even use conventional lenses to focus the stuff.
And this brilliantly illustrates just how far into the realm of science fiction ASML had to push. To even generate this delicate EUV light, the solution is just mind-blowing. Step 1, you fire incredibly powerful lasers. Step 2, those lasers hit microscopic droplets of molten tin, tens of thousands of times every single second. Step 3, each tiny impact creates a burst of plasma that is actually hotter than the surface of the sun. And finally, step 4, because you can't use glass lenses, that light has to be bounced and reflected using perfectly polished mirrors. And the whole shebang has to take place inside ultra-high vacuum chambers. Because yeah, even normal air would absorb the light before it ever reached the silicon wafer.
Now, take a step back from that microscopic plasma for a second. We are talking about subatomic precision here. But the machine required to execute this microscopic dance is massive. A single EUV machine weighs well over 150 tons. To put that into perspective, that's roughly the weight of a full-grown blue whale.
And the complexity doesn't stop at the weight. Each one of these systems contains more than 100,000 individual parts. Just to get this to a customer, it must be transported in hundreds of carefully managed shipments, only to be totally reassembled at a fabrication plant. Because of this absolutely unparalleled complexity, the most advanced systems cost hundreds of millions of dollars each.
Obviously, you don't build something like this alone. Developing this technology required one of the largest collaborative engineering efforts in modern industrial history. ASML worked with suppliers and research institutions all over the globe. The German optics company Zeiss developed some of the world's most precisely polished mirrors, where surface imperfections are literally measured in fractions of a nanometer. American firms contributed incredibly advanced laser technology, and ASML in the Netherlands handled the master systems integration and engineering. Thousands of engineers solved problems that had never been encountered before. And that intense collaboration, it built a technological moat for ASML that is measured not in years, but in decades.
Now, what's really interesting about this is how the entire cutting-edge tech industry bottlenecks right here. Today, every single leading-edge semiconductor manufacturer absolutely relies on this EUV technology. TSMC uses it to manufacture the wildly advanced processors for Apple and NVIDIA. Samsung depends on it for their most advanced memory and logic chips. Intel is investing heavily to build brand new fabrication facilities entirely around this same technology. Without ASML's machines, not a single one of these companies could manufacture the smallest, fastest, and most energy-efficient processors that power our world today.
And this directly fuels the absolute biggest trend in the world right now: artificial intelligence. The AI boom has made ASML's machines infinitely more valuable. Think about the chain reaction here. Training advanced AI models requires enormous computational power. That power strictly relies on increasingly sophisticated chips. Those chips require cutting-edge manufacturing. And, as we just learned, cutting-edge manufacturing entirely depends on ASML. So as global AI investment has accelerated, so has the massive demand for these exact machines.
Because of this outsized importance, ASML, a company that is at its core just a group of brilliant engineers, has suddenly found itself thrust directly into the center of complex geopolitics. Governments worldwide began to view advanced chip manufacturing not just as an economic advantage, but as a deeply critical matter of national security. Advanced chip making is now the subject of strict industrial policies, global alliances, and severe export controls. In fact, ASML's products are so strategically significant that sales of certain advanced systems are outright restricted by governments. It's a pretty remarkable shift, honestly, showing how a behind-the-scenes engineering firm is now front and center in global conversations about national competitiveness and economic resilience.
So the crucial point is this. Beyond all the incredible physics and high-stakes national security implications, ASML's greatest lesson might actually be about patience. This defining technology didn't just happen in a single overnight breakthrough. It required decades of relentless research. It required long-term partnerships, enormous financial commitment, and a willingness to pursue a goal that many top experts explicitly stated was unattainable. In an era where businesses are so often obsessed with rapid growth and quarterly results, ASML is the ultimate proof that the world's most valuable innovations are built through persistence, not just speed.
There's a quote from our source material that really sums it up perfectly. Without ASML, the digital world would still exist, but it would be moving forward at a much slower pace. They don't create the world's smartest chips. Instead, they patiently and meticulously built the extraordinary machines that make those chips possible, easily making them one of the most absolutely important companies of the 21st century.
Which leaves us with this final, pretty massive thought. We constantly hear the names NVIDIA, Apple, Microsoft, and Google when we talk about the future. But after looking at the staggering complexity of printing with extreme light, the decades of impossible engineering, and the fact that every single cutting-edge chip must pass through their machines, when you think about who controls the future of artificial intelligence and global technology, who do you think really holds the keys?